Welcome. This video discusses vectorized functions in R. We've talked about this idea of using for loops to streamline our code. For loops are wonderful for avoiding the idea of having to copy and paste the same chunk of code over and over again. However, they are kind of slow in R. So if you have any kind of tasks that is very computationally expensive, you probably don't want to be doing it over and over again in a for loop. Instead, what you want to do is use something that's called a vectorized function. And the idea is that R is what's called an interpreted language. So this goes back to some of the ideas about object-oriented programming. Whenever I run a function on an object, R is determining which version of that function to run. So it has to do some sort of computational overhead. So for instance, if I was going to do a for loop and compare each one of my numeric values to 10, so is it greater than or equal to 10 or not? It would have to go through and at the first iteration of that if statement say, oh, okay, I'm comparing something to 10, it's numeric. All right, let's go ahead and do that comparison. Goes to the second one. What kind of thing am I dealing with? Oh, it's numeric, so let me go ahead and do that computation. And so it has to do that little bit of overhead each time it runs. If instead you use something like a vectorized function, it does that sort of overhead once and then runs all the code. And so while it's still sort of looping underneath, it's just doing it in a much faster way. There are a lot of built-in vectorized functions, which is wonderful. So you don't have to write your own vectorized functions. There are things like call means, which will take a numeric matrix and return to you the means of each one of the columns. Same thing for row means. Call sums, row sums. Basically, most any of the common numeric summaries that you're going to do exist in a vectorized form. Some of them, though, you do need to grab a package. So you would need to install the matrix stats package to gain access to call medians and call SDs. Remember that this notation is saying from the matrix stats package, grab the call medians function. We did see a vectorized version of if else already through the dplyr package, if underscore else. And so we'll recap that one here as well. And then we're going to discuss this idea of the apply family of functions, which is a really nice base R method of doing pseudo vectorized functions. We won't discuss the per package. This is part of the tidyverse, but it's a package that I think is a little bit difficult for beginners to use. So I like to start with the apply package, and then you can learn the per package once you get your feet wet with that. So let's just start with some examples of these vectorized functions for finding summary stats. Again, call means just is going to take in a numeric matrix or data frame and return the means of each one of the columns. For instance, we can read it back in that wine data set here, and then I'm going to get rid of that non-numeric column, right? Type is red or white, so I'm going to remove that column from it, and then I'm going to apply the call means function to that. And it's a very quick way to return all of the means of each one of my columns. Similarly, as long as I've read in the matrix stats package, I can use call medians. One issue with call medians, though, and all of the functions from matrix stats is that they require a matrix, not a data frame. So again, these functions from matrix stats, they require a matrix. And so what we're going to do here is take the wine data set, remove that non-numeric column, and then explicitly coerce this thing to a matrix. That function, call medians, it's not going to do that for us, so we're going to go ahead and do it first, and then pass that to call medians. And we'll get the medians of each one of those columns. All right, we talked about the idea of if underscore else as a way to do vectorized if else logic. And here was the basic syntax for this if else function. We say if else, and then we give it a vector of conditions of true false values. And then for any one that's true, this is the code that gets evaluated. For any of those values that was false, this is what gets evaluated. And we've already created one variable using this kind of logic. Let's go ahead and just do another one with this wine data set. So we're going to take the wine data set object, we're going to overwrite it. And what we're going to do is take it and create a new variable. So remember, mutate from dplyr adds a new variable on your data frame. And that new variable is going to be called QualityCat. And so we have this quality variable that measures how good the wines are. And what we're going to do is just break it down into different groups. So if else, we're going to give it a vector of conditions. And so anywhere where those conditions resolve as true here, we're going to return poor. Anywhere where it resolves as false, we're going to run another if else to see if it's less than or equal to 5. If that's true, we're going to assign OK. If that's false, we're going to do another if else. If that's true, good. If that's false, we're going to do another if else and apply great. And if none of those were met, we're going to say error. This is like a catch-all. All of our qualities were somewhere between 0 and 10, so if it wasn't met there, then it must have been like a missing value or something weird going on. So we're just going to return error. To see this new variable that we've created, we'll just use the select function here, line data, select quality, and QualityCat. And so we can see that these values do match up with the logic that we were writing up here. Okay, so those are some of the built-in vectorized functions and that if-else function from dplyr. Let's talk about the apply family of functions. So the apply family of functions is really useful for applying a function to each one of the rows of a data frame, each one of the columns of a data frame, or to each element of a list, those kinds of things. So let's start with apply. We say that this is the apply family of functions because there are functions like apply, lapply, sapply, vapply, mapply. We'll just look at a couple of these that are the most used ones. Apply can be used to find column summaries like we were doing before. Here are the different arguments to apply. So X here is the numeric data frame or array object that we're going to apply the function to. And so since we're going to do column summaries, we're assuming that the data here is going to be numeric. So again, X here, capital X is the argument. This is the numeric data frame or matrix that we're going to apply our object or our function to. Margin corresponds to which dimension of the data frame or matrix or array that we want to apply the function to. And so usually we're going to do margin equal 1 or 2. If we do 1, this is the rows. If we do 2, this is columns. And the easy way to remember that is if you've ever looked at matrices before, you know that we always say that they are like a 3 by 5 matrix. So we always do rows by columns. So 1 is the first thing that you do, so the number of rows, and then 2 is the second thing, columns. So if I want to apply a function to each row, I use margin equal 1. If I want to apply a function to each column, I use margin equal 2. Fun equal is the function that we want to apply to the rows or columns. But one thing about fun is we don't call it like a function, we just name the function that we want to use. And so what I mean by that is we don't call it with parentheses. So we'd say something like fun equal mean, but we wouldn't put fun equal mean with parentheses. So not something like this. So we're just going to name the argument there. But of course, there might be other arguments that we want to pass to this mean function. So how do we do it if we're not calling it sort of as a function here? Well, what we do is we just pass any other arguments through this ... this unnamed arguments bit here. So we just put any other arguments that we want to pass to our function after this comma. So for instance, I would do something like fun equal mean. I would just put a comma and I could put something like na.rm equal true with all the other stuff around it. So this is the way that we would pass extra arguments to whatever function we call here. Let's look at an example here. Suppose that we do want to call, say, this summary function for each one of these numeric columns. Well, the first thing I'm going to do is just remove all of the non-numeric columns from my wine data. So wine data, select, let's get rid of the type and the quality category variable that we created. So everything in here is now numeric. And so I'm going to apply to that object that we just returned there the function summary to the margin 2 to the columns, right? 1 is to each row, 2 is to the columns. So apply to this object, to each one of the columns, the function summary, but then let's also apply the na.rm equal true argument to summary. So this is being applied to this function here. And this apply function will then do that. So every column now gets the summary function applied to it, and this comes out looking a lot nicer than if I just ran summary that object na.rm equal true. If I just ran this, the output doesn't look as nice as what we have here. So this is a little bit better way to do it. Okay, so that's one really commonly used apply function. Another one is what's called lapply, and it has the L in front because L stands for list. So lapply applies a function to each element of a list. As you remember, a list is just one-dimensional, right? And so if it's one-dimensional, I don't need to specify the margin, right? Margin was to say, do I want to do it to the first dimension or the second dimension or possibly third, fourth, etc. There's no dimension here because well, there's only one dimension here, there's not two, so we don't need to apply a margin argument to this function. All we need here are x, which is the vector or list that I want to apply the function to, and then fun is the function to apply. Just like before, I'm going to name that function, but I'm not going to actually call that function, so any other arguments I want to pass to it, I pass through the dots. So here's an example. I'm just going to create a basic list, so a list with 3 elements. So 3 elements here. I have a bunch of random normal values, so I have 100 random normal values in my first list element. I have 25 random uniform values in my second, and I have 500 random values for my what's called a gamma distribution in my third list element. So it's a list with 3 vectors in it. If you look at the structure of the list of this object we just created, it does say that it is a list, so that's good. And then it says that we have this many values, right, for each one of those. All right, let's say I want to find the mean of each one of those. Well, I can use lapply and say apply to each element of this list. Which list? X equal my list. Apply to each element of that list the function mean. And so that's going to return to me the mean of each one of those vectors up there. And you can see that this returns it as a list, right? This returns the result as a list. And that might not be ideal because in this case, you could easily put these 3 things in a vector and it would make sense to do something like that. So there's another version of lapply that's called sapply, which is just like lapply except it simplifies what it returns if possible. So S just stands for simplify. I want to sapply instead of lapply. I'll do the same exact function call except change this to S, and it tries to simplify the result and it says, oh yeah, I can simplify what we did there into a vector. And so I'm going to go ahead and do that for you. And then one more function from the apply family that I want to talk about, although it's not like something apply, it is part of the apply family, and that's replicate. And so replicate is great if you just want to run the exact same chunk of code over and over again without changing anything. Before, when we were doing for loops, we were changing that code over and over again, we were running that same code over and over again, but we were changing something each time. Replicate is really great when you just want to run the same chunk of code over and over again. And so there are only 2 arguments that you need to give replicate. And one is the number of replications, and the other is the expression to evaluate repeatedly. This is really useful in what are called simulation studies in statistics, which we do quite a bit. So I'm just going to give you a very basic example of estimating a probability using this replicate function. So let's suppose that we're going to select 5 letters at random, and we want to know what is the probability that none are repeated. Well, the idea of probability is just one interpretation of probability is in repeated samples, how often does this thing occur? So how often does the event of interest occur? And not just how often, but what frequency. So I should say, what frequency? How about in what frequency does this event occur? So essentially we're going to look at the number of times it occurs divided by the total number of trials. That is one way to look at probability. And what this means is that essentially I can just create a whole bunch of trials and just look at how often the event I have an interest in occurred, divide that, and I'll get the approximate probability. So if I want to approximate a probability using R, I just need to find a way to create the trials and then find a way to check how often my event of interest occurs. And so there's this sample function in R, which is really handy for taking a vector or an object and pulling elements from it at random. So here I'm going to say, let's do a sample of size 5 from the letters from the letters object. Remember that letters is just a vector of A through Z. And I'm going to put replace equal true, which means that I can get the same outcome more than once. And that's important because that is exactly what I want to be looking at. So I'm going to select 5 letters at random, and I want to know what's the probability that none of them are repeated. So one possible sequence would be A. It's not a likely sequence, but it is a sequence that could happen. So by running this sample code, this gives me a way to simulate the process of selecting 5 letters at random. Here are 2 calls to sample, and sample is going to do this randomly using a random number generator, and so I'm going to get different values each time I run this. And what I want to do is just see, well, how often do I get all unique values here. You can see in this case, I got 2 z's. So with this group of 5, I got a repeat. How often do I get repeats? Well, like I said before, really what we want to do is check how often we get unique values, that all the values being unique. And so there is a unique function in R that can help us out here. What I'm going to do is first set the seed, and this is just going to make my results reproducible. And so we said that what we wanted to do was use the sample function, which uses a random number generator to get random values back. Well, by setting the seed, you are setting that random number generator to start at the same values each time, so you're going to get the same random draws. So these are really pseudo-random draws. They're not actually random draws, of course. So this is just going to make our results reproducible. I'm going to go ahead and sample 5 things from that letter's argument with replace equal true, and then I'm going to run the unique function on the result of that. And so unique will return all of the unique elements from that vector that got returned. If that thing is of length 5, that means that I had 5 unique values. I had no repeats. So what I'm going to do is take the result of unique and then look at the length of it. If that length is 5, no repeats. If it's less than 5, I had some repeats. And so here we go. What we can do is then just compare the result of that to 5. If it's true, again, no repeats. If it's false, I had repeats. And this is the exact code that I would want to repeat to rerun this trial over and over again, right? So now I'm going to do sample, unique, length, and then see how often it's 5. And I'm going to rerun this code 5 times, right? So replicate is going to rerun the same chunk of code over and over. So I'm going to say replicate or rerun this code down here 5 times. And so I had no repeats in 3 of these 5. But in 2 of the 5, I had repeats. So what's the probability that none are repeated? Well, only looking at 5 trials isn't really great. What we could do is just repeat this, say, a really large number of times, and then look at the proportion of repeats that we get. And one thing that you should know about R is that whenever you run a numeric function or try to add something or do some sort of math to a true-false value, it coerces the trues to 1s and the falses to 0s. So if I have this vector of true-false values and I look at the mean of it, it's actually going to look at the proportion of true values. And what that means is that this is exactly the kind of thing that I wanted to look at when I was thinking about the number of times this event occurs divided by the total number of trials. That's what a proportion is, how often that thing occurs divided by the total number of trials. And so this is going to give me a way to easily determine the probability that none are repeated. All I need to do is up my replicate number to, say, 50,000. This is going to give me a pretty good approximation to this probability. So I'm going to repeatedly run this chunk of code 50,000 times, and I'm going to store that. I'm going to then take the mean of the result of that call, and I get that approximately 62.3% of the time I get no repeats. So again, replicate, although it doesn't look like an apply function, this is in the apply family of functions. Let's jump into R and play around with these vectorized functions. Welcome back to R here. We're going to go ahead and try to do that same exact task we did with the for loop previously using the apply functions. And so what we were doing before was we were fitting a bunch of different simple linear regression models, but for different predictors. And so you can see that how we're going to have to change things is through this formula that we're giving the LM function. This is the first argument which specifies the model that I want to fit. And let's go ahead and look at the help for LM, just to get a little bit better idea what's going on here. So this LM function fits linear models, and the first argument is called formula, and it's got to be an object of class formula. And so remember that classes are something that are associated with data structures, and so there's a specific data structure in R that is a class formula. And so we need to go ahead and basically create a bunch of formulas where this variable changes each time. Let's go down here and start trying to do that. So the first thing we need to do to switch this from a for loop to using the apply family is obtain a list of formulas, or formulae, I don't know, to apply the LM function to. Let's throw in an R chunk here, and we'll go ahead and try to create our formulas. Let's start with the paste function. So really what we want to do is have these formulas that look something like the quality variable, tilde, and then we want our names here. So we would want something like fixed acidity being first. So we can paste those two things together. What's kind of nice about this paste function is if you actually give it a vector of values over here, so if I have fixed acidity, and I think another variable was total acidity, if I remember correctly. If you give it a vector within there, it's actually going to paste each combination of those together. So it's going to do quality with fixed acidity and then quality with total acidity. And so really all I need to give over here would be the entire vector of names that I want for predictors. And we'll set up these character strings that look a lot like formulas. So let me just copy this, paste it down here. And instead of having fixed acidity here, we'll grab the names using the names function. So the names of my wine data. And then we're going to remove the non-numeric and the response variable. So if I run that, I now get a vector with character strings that look like formulas. Now these do not have class formula though, and so what I need to do is coerce them to formulas. So there's this as.formula function, which will allow us to coerce these things into formulas. So I could take, for instance, as.formula and give it this character string up here, and that is going to return to me an actual formula. Notice that this returned a little bit different. It doesn't look like a vector being printed out. This is a formula associated in R. So that's an object that has a special class to it. And so really what I want to do is take this as.formula function and apply it to every element of this vector. Well, lapply will do that for us, right? Lapply applies a function to every element of a list, but vectors are one-dimensional, lists are one-dimensional, so you can actually use lapply on a vector as well. So I'm going to go ahead and do lapply. My x, the object I want to apply my functions to, will be this guy right here. Oops, I don't want to cut, I just want to paste or copy. And so the function I want to apply then will be as.formula. And again, I don't specify this function with parentheses, I just name the function that I want to call. And if I do that, I get back out a vector with a bunch of different formulas in it. So now I have every formula that I want to send to the lm function. So our next step is now use lapply with these formulas or formulae and the lm function. Go ahead and create a new R code chunk. We'll grab that code that we just ran up here. I'll go ahead and save this. This is going to be a list, remember, as the output. I'll call this my formulae. Sure. Fix this spacing. Okay. There we go. Sorry, bad spacing just bugs me now. All right, so now I have this object my formulae, which is a list with a bunch of different formulas in it. So now to each element of that list, I want to apply the lm function. So if I want to apply functions to a list, I use lapply. The x value that I want is my formulae. And the function I want to apply is lm. Again, I don't use parentheses after lm. I'm just going to name the function I want to call. But when I called lm, do remember that I needed more arguments. So I also needed to add in the data argument so it knows which data set to pull these variables from. So I'm just going to give that to the lapply function after a comma. Oops. So we'll do data equal my wine data. And this should return a list with all of the simple linear regression fits. So I'll go ahead and call this my fits. Run that. And now if I want to get the coefficients out of each fit, I could think about doing, I want to do coef my fits 1. That's the first list element. So those give me the coefficients for fixed acidity being used as a predictor. Well, really, if I want to get all the coefficients out of my model, I want to apply the coef function to each one of my list elements. And so I can do that as well. I'll go lapply. My x will be my fits. This is my list of linear regression fits. And then my function I'm going to apply is just the coef function. I run that and I get a list returned of each one of the intercepts and slope terms. But, that's not ideal. Maybe I want to return that instead as a vector or a matrix. So return in a simplified way. remember that we can return it in a simplified way using sapply. So we'll sapply, we'll do the same exact function call. So we'll do myFits fun equal coef. And again, this is going to try to simplify the result that it returns. And so it does simplify the result into a nice looking little matrix here, but it doesn't really name this thing quite correctly, which is a little disappointing. Let's go ahead and save the result of this as like my coefs. Oops. And we can get an idea of how to change that pretty easily. So we'll do my coefs. We know about this structure function. So where are these row names coming from? Well, they're coming from an attribute called dim names. And a lot of the commonly used attributes have a function that will help you get at them. So if you look at the dim names function, you can actually run dim names on my coefs. That'll allow you to see them and also modify them. And so if I did want to change the row value that was corresponding here, we have seen this kind of output before. This is a list, right? This is the first list element. This is the second list element. So if I go in and I get the first list element, I can actually overwrite that with my own character vector. So I can say intercept slope. Now if I look at my coefs, that looks a lot better. So now I would also probably want to change the other dim name so that I know what columns these are. Go ahead and copy that same code. I'm going to switch to the second list element here because that was the column values. And instead of this, I'll go ahead and just use names of my wine data. But again, we need to remove 12 and 13. Let me run that. Now if I look at my coefs, this looks a lot better. So a lot of post cleanup there, but you can see how the lapply function and sapply functions can be used here to do the same thing that the for loop did. To recap, we can now improve our coding by using either for loops or vectorized functions. And vectorized functions are great because they're a lot faster, and they might be a little bit difficult to figure out at first, but this apply family is really great. And then if you really get into doing that kind of coding, there's this per package that's part of the tidyverse, and they have a lot of helper functions and extension functions that are very, very useful for doing the exact same types of computations.